Hi everyone, I'll talk about applications of learning theory in identifying treatment effects. This is joint work with Yagsai, Alkis Kalavasis, Katerina Mamli, and Manolis Zempetakis. Let me begin by defining what an observational study is. In an observational study, we observe several individuals with different features and or covariates. These features divide individuals into groups. For instance, here the feature age divides individuals into two groups, the group of young people and the group of old people. In addition to this, individuals also have treatments. For instance, here it denotes whether the individual smokes or does not smoke. It's kind of ironic that we use treatment to denote smoking, but this is the terminology we are stuck with. So, unlike in a randomized controlled trial, the treatment assignment in an observational study is not randomized across individuals. Instead, it's a decision that is determined by several features of the individuals as well as environmental factors that may or may not be observed. Finally, individuals have outcomes and are such as whether they are healthy or not, and our goal is to understand what is the effect of the treatment on the average outcomes of the individuals, or more specifically here it means what's smoking's effect on individuals' health. So there are many ways to measure what a treatment effect is. Here we'll focus on the average treatment effect, which is defined as the difference between the average health of the individuals in two extremes, one where everyone smokes and one where no one smokes. So as I mentioned, there are many other types of treatment effects. We'll focus on the average treatment effect in this talk, but our techniques extend to these other treatment effects as well. Now, before going into our results and prior works, let's talk about why a naive strategy for estimating the average treatment effect does not work. Perhaps, suppose we observe these individuals, some of them smoke, some of them do not. A simple way or a simple estimator for the average treatment effect is to partition individuals into two parts. One which consists of all the individuals that smoke, and the other consisting of individuals who do not smoke. And then say the estimate of the average treatment effect is the difference in the average health of the individuals in these two parts. In this example, this would tell us that smoking has no impact on the individual's health. This does not feel correct, plus this approach is fundamentally wrong because the choice of whether an individual smokes is in general not an IID, is not randomized, and instead is determined by different covariates of the individuals. And in this particular example, we indeed see that if we were in a setting where we could observe both outcomes for an individual, that is, could observe their health when they smoke and when they do not smoke, then we can estimate the true average treatment effect and see that smoking does have significant adverse impact on individuals' health. So this is a core point of distinction between identifying treatment effects and other more standard learning theory problems such as classification. Here, even if we are given the precise data distribution, because of this censoring, where we only observe one outcome for each individual, treatment effects are in general not identifiable unless we make some assumptions. In contrast, in the classification setting, if I describe the precise data distribution of X and Y, then an optimal classifier is always learnable from the data. So since we require some assumptions to identify the average treatment effects, existing literature in causal inference proposes several simple and sufficient conditions that enable identification of the average treatment effect. Now, these are sufficient conditions, and it's long known that they are not necessary. In fact, this question dates back to at least the work of Rubin in 1977, where he mentions that when these assumptions are violated, certain parametric properties of the distributions could potentially be used to identify average treatment effects. In learning theory, we always like to characterize the precise settings where we can solve problems using various dimensions. And the first result in our work is precisely this. We characterize the observational studies where the average treatment effect is identifiable. This characterization is interesting because the simple sufficient conditions that people have proposed in the literature can be easily violated in practice, and in fact this is a core reason why several frameworks that relax these assumptions have been proposed. And in these relaxed frameworks, existing methods can approximately identify the average treatment effect, or they can identify an interval in which the average treatment effect is guaranteed to lie. In contrast, our results enable the exact identification of average treatment effects in several of these frameworks. So in this sense, our characterization for identifiability of the average treatment effect acts as a bridge between causal inference and learning theoretic tools. So next, let's try to understand what these sufficient assumptions are. As I mentioned before, the core challenge in identifying the treatment effects is that the decision of whether an individual smokes or not is not randomized, but depends on various features of the individuals which may or may not have been observed. So the first assumption people make to ensure identification is unconfoundedness. And what unconfoundedness requires is that conditioned on the observed covariates of the individuals, the decision whether they smoke or do not smoke is randomized. So for instance, if the only feature that we observe for the individuals is their age, then we can partition individuals into two parts, young and old. And then in the young group, the decision of whether an individual smokes or not is only determined by a coin flip and not any other unobserved features of the individuals. Note that while within each group, the treatment decisions are decided by a coin flip, the bias of this flip of this coin can be different across different groups. The second assumption people often require is overlap, and this roughly requires that for each unique feature value, there is at least one individual who smokes and at least one individual who does not smoke. So for instance, here the group of young people violate the overlap assumption because there is no young individual who smokes, whereas the group of old individuals satisfy the overlap assumptions because we have both old people that smoke as well as old people who do not smoke. The issue with these assumptions, of course, is that they're very easily violated in practice. So let's see one example of this with unconfoundedness. As I've been hinting, if there is some covariate that affects the outcomes of the individual as well as their decision to take up the treatment or not, then this variable can cause unconfounding to be violated, or it can cause certain confounding between the outcome and the treatment decision. And in our running example, one such covariate could be the socioeconomic status of the individuals, which is known to affect both health and tendency to smoke. Apart from this, there are many other reasons both unconfoundedness and overlap can be violated, which I'll not go into here, but they are detailed, they're discussed in detail in the paper. Okay, so with this, I'll proceed to some of our results, starting with setting up some notation in a learning theoretic framework. So it turns out that to get to our identification condition, it's sort of important to pick the right factorization of the data distribution. And we in particular factorize the data distribution into two marginals. The first marginal is distribution over feature and outcomes. And the second marginal is the probability of assigning a treatment conditioned on the feature and outcome. We call this latter marginal the generalized propensity score. Now, here is where we introduce some new notation in the area of causal inference, clearly inspired by work in learning theory. We'll introduce two concept classes, one for generalized propensity scores and the other for these feature outcome distributions. And then we say that an observational study is realizable with respect to the tuple P and D if the corresponding propensity score belongs to the class P and the corresponding feature outcome distribution belongs to the class D. In this language, now our question is to characterize the tuples P and D, which enable the identification of the average treatment effect. Our main result is precisely such a characterization. It says that the average treatment effect is identifiable if for any two distributions in the class D, the ratio of their densities is not equal to the ratio of any two generalized propensity scores in the class P. As is mentioned on the slide, there are some other mild conditions also required in this identification conditions, which I'll not go into here and again are explained in the paper. So this is an identification result which allows one to use infinitely many samples, but under a quantitative strength achieve estimation results for the average treatment effect from finitely many samples. And here the estimation error scales polynomially with the number of samples and with some dimension of classes P and D. Okay, so let's now go into some applications of our main result to scenarios. The first scenario is the standard one, where both overlap and unconfoundedness are satisfied and where average treatment effects are known to be identifiable. Here our results present an alternative proof for the identifiability of it. But apart from this, we consider three other scenarios where one or both of unconfoundedness and overlap are violated. I'll discuss the second scenario in more detail on the next slide, but I'll quickly mention that the third scenario, where unconfoundedness is satisfied but overlap is violated, is also widely studied and has been deployed in impactful economic studies. With that, let's dive into the second scenario, where overlap is satisfied but unconfoundedness is violated. So if you're not familiar with some of this work, all I want you to take away from sort of this slide is that this scenario can capture certain models which are called sensitivity analysis models in the literature. In these models, there's a parameter gamma that parameterizes the distance of an observational study from unconfoundedness. Roughly speaking, this can be thought of as some analog of an adversarial model in causal inference. And here existing methods can identify the average treatment effect up to some factor that scales with gamma. In contrast, if you are willing to assume that the outcomes follow some standard outcome model, such as a generalized linear model or something slightly weaker than that, then using our techniques, you can exactly identify the average treatment effect even when gamma is very, very large. So with that, I'll conclude. In this work, we introduced a learning theoretic framework that connects causal inference, or specifically treatment identification, to learning theory. And it's very interesting to see if learning theory can have other applications in causal inference. Some other questions, which are some other smaller questions which are directly related to our work, are as follows. Our estimators are computationally inefficient and based on certain covers of the classes P and D. It would be very nice to have efficient and loss minimization based estimators. It would also be great to achieve some form of robustness to misspecification in the choice of the classes. And finally, it's very interesting to see if these new results can lead to better evaluations on real world data. With that, I'll conclude. Here are the references, and thank you for your attention.